Okay, so we're going to prove the rational roots theorem. The first thing we want to do is we really want to thoroughly read what the rational roots theorem states and understand each piece of it. So take some time, pause the video if you need be, read what this theorem states, and then unpause, and we're going to start going through it together. Okay, so now that you've read it, hopefully, and you really sat there and tried to make sense of all these pieces, and it's okay if you don't understand all the pieces, because I'm going to explain them right now. So the first thing is we're going to talk about it being a polynomial, right? We want f of x to be a polynomial. That just means that this here is some positive whole number, or a positive integer, this n value. Now, the next thing it says is that the coefficients are integers. So that means that this a sub n minus 1, and all of these coefficients going down, a1 and a0, they're all integers. So that means that they belong in this set. The integers are written like with this z, with the double line, and they look like this: 0, 1, and then -1, right? 2 and -2. And then they go off forever like this: 3 and -3, 4 and -4, 5 and -5, so forth, right? These are all your integers, we say. So these things, right, a sub n is some member of this set, right? Is one of those, and a sub n minus 1 is another member, and so forth and so forth. And these are the coefficients. This is saying the coefficients are integers. Now the next thing is the hypothesis, what we're essentially given. We're given that p and q are integers. So that means p and q also are some members of this set. They might be, p might be 2, q might be 5, so forth. And then we have it, so p and q are integers, and then we have another condition, that p over q is in simplest terms. And what that means is that p and q share no factors. So let's just equate this, and let's say right away that if p over q is in simplest terms, p and q share no factors other than the trivial factor of 1. Share no factors. That's what this means. Share no factors other than 1. And this is going to be an important condition that we have here. Then the last condition is that p over q is a root. P over q, when I plug in if I plug in p over q in for x, right here, then everything, this whole polynomial is going to equal 0. And what the conclusion is then it must be the case that p is a factor of this constant term at the end of the polynomial, and q is a factor of the first term, or the first coefficient, right? That first coefficient, a sub n. And we want to prove this. And what do we want to do when we prove? Take your time, start with have a theoretical roadmap for your proof in your mind. So the first thing is that you want to start off with all of these conditions, this here. These are the conditions you start with. This is in geometry, or maybe you call this the given, right? This is what's given, and you want to make a chain all the way to the conclusion. You want to make an argument all the way to the conclusion. So we start off with what's given, and the first given that we're going to start off with is that f of p over q equals 0, okay? Now, this implies that when I plug in p over q into this polynomial, I'm going to get 0. So we're going to start off with that. Instead of writing x in this, we're going to write p over q. So I'm going to say, I don't know what's going on here. Uh-oh, and can I get out of it? Let's see. Oh, something went wrong. Let's see what we got. Okay, so if I start writing, what I'm going to have is a sub n, and then instead of writing x, I write p over q to the n, plus a sub n minus 1 to the p over q to the n minus 1. And then I go down, all the way down to a sub 1, p over q to the 1 plus a sub 0. All of this has to equal 0, because I just substituted for what this is with this, right? Okay, now here's the first, where we gotta just, be a little clever with our algebra part, right? So I'm going to do that in green, and I'm just going to put it anywhere. So basically, we need to see that for each of these, P over Q to the M, whatever it is P to the M over Q to the M, right? That's first, and you should just convince yourself of that with just taking examples, right? What does P over Q to the M means? It means P over Q times P over Q times P over Q. How many P's are being multiplied on the top? M P's are being multiplied on the top. How many Q's are being multiplied on the bottom? M Q's are being multiplied on the bottom. So this identity should be, easily understood. Then the next thing we want to see is we want to see that, like, if I do Q to the N over Q to the N minus 2, we want to remember our rules for dividing like bases. And these are like bases. You have a Q. What's the rule? You subtract the exponent. So it's Q to the N minus 2. And you just have to remember that you want to put that whole other one in parentheses, distribute the minus correctly to get that this is going to be Q to the second, right? With that fact, okay, we're in a position to start, okay? So the next thing that I want to do now is I want to multiply this whole polynomial by Q to the N on both sides. And we want to keep in mind that Q is an integer, right? Right, Q is an integer, but we'll worry about that in a second. So Q to the N over here, Q to the N over here, right, times this whole thing. Okay, and I'm just rewriting. And then if I multiply 0 by Q to the N, I still get 0. So on the right-hand side, everything stays 0, and all I did was multiply by Q to the N over here. And now I have to distribute. So when I distribute in, right, every single term, you want to go to every single term, all the way down. And the hardest part about this is how general it is, right? You're not dealing with any real numbers. You got to figure out what's going on. So I'm going to rewrite this now as Q to the N times P to the N times Q to the N over Q to the N. And we see that these two things are the same, so they're going to cancel out. And I'm left with A to the N times P to the N as that first term, plus A to the N minus 1, P to the N minus 1, times Q to the N over 1, over Q to the N minus 1. These two cancel out, leaving a Q in the top. Plus dot, 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 dot. And if you see a pattern, there's no Q's here. There's Q to the 0 right here, which is just 1. This is Q to the 1, and then so forth. And it's going to go down, and when I distribute all the way the Q to the N from here, all the way down to the A1, P to the 1 times Q to the N over Q, this is Q to the 1, and it just gets subtracted, so it's just Q to the N minus 1 here. Plus A0 times Q to the N equals 0. Okay? Now, with this here, I'm going to rewrite it back at the top. I'm going to just erase real quick. So we have that. That's okay. Okay, we should know what the theorem states. And I'm just going to bring this up. So let's bring this up. Let's take this and let's rewrite it a little bit neater. So I'm going to have A sub n, P to the n, all left over when I distribute that Q to the n, plus A sub n minus 1, P to the n minus 1 times Q1, plus dot, 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 all the way going down to A to the 1, Q to the n minus 1, times P to the 1, I forgot the P to the 1, but it doesn't matter the order, plus A0 times Q to the n equals 0. And this here is what you kind of want to manipulate and just get your result, okay? What you have here is that everything, all of these are integers, right? We started off with saying that A sub n is an integer. P is an integer, so then P to the n is some integer. So this is an integer, this whole term. And you could make a similar argument saying that this whole term will be an integer. And all the terms are integers. And of course, the sum of two integers or three integers or n integers is another integer. So that means that this whole thing is an integer. And that's a key realization, right? Okay, we have to see that. If you don't see that, you're going to be in trouble. That this whole thing is an integer. Now, and it equals 0, obviously, but every one of these pieces is an integer as well. That's also important. So now, if we take that as, if we see that as a condition, that this is, of course, an integer, it's equal to 0, so that's an integer. But it's also that each term is an integer. This is an integer, this is an integer, this is an integer, and so forth, going down. With that fact, we can get our result. Our result is as follows. If I divide everything by p, let's start off by dividing everything by p. So when I divide everything by p, I get p to the n minus 1 plus a sub n minus 1, p to the n minus 1 over q to the 1 minus 2 now, because I divided by p. Look, I'm dividing this by p. The exponent goes down by 1. It was n, now it's n minus 1. It was n minus 1, now it's n minus 2. Plus a1 q to the n minus 1, and then p to the 1 divided by p cancels out, so there's nothing left, plus a0 q to the n over p has to equal 0. And with this, you get one part of your result. You get that this whole thing is an integer, right? This whole thing must be an integer. For the same logic that we had above, look, p is an integer, a is an integer, and p to the n minus 1 must be an integer, and then this is an integer. An integer times an integer is another integer. So then, therefore, this is an integer. And then you could make the same argument for this thing over here, and so forth, for every term except for this last one. This last term is key. This last term is very key, because what you have here is that you have a0 q to the n over p, right? And if this whole thing is an integer, and then this has to be the negative of that integer because you have it equal to 0, this must be an integer. And we have to convince ourselves. You have to say, right? This must be an integer. Okay? And with this being an integer, right? This is q to the n, a0 q to the n over p, right? The only way that this is an integer is if p is a factor of a0. Why? Because p and q share no factors. So then p and q to the n will share no factors. So let's erase, let's break this down. Let's break down our argument for this first part, because it's the same argument for why q divides a sub n, which we're going to do in a second. So we have a0 qn over p must be an integer. Okay, why? You should make an argument why. Why is it? This is an integer. This is an integer, this whole thing here. Okay? And if you even minus it over the other side, if I minus this onto the other side, right? Then I'm going to get this whole thing is equal to this negative thing right here. And this whole thing is an integer. So then that means that this thing on which it's equal to must also be an integer. You can't have something be an integer and not an integer. So if I minus this on the other side, I'd have this minus q to the n over p. So that's a good argument saying that this must be an integer. Now, since this must be an integer, q and p share no factors. From what we're given that p over q share no factors, this implies that q to the n and p share no factors. And the only way that this is an integer is if if P is a factor of A sub 0. Okay, we should just convince ourselves, or we should just go through this and why this is true, right? If these two don't share any factors, Q doesn't divide, or P doesn't divide Q to the n. P must divide A sub 0, right? If I have, so to put it in another more simple terms, if I have A over B, A times B over C is equal to some integer D, and I know that C is not a factor of B, that must mean that C is a factor of A. Okay, I'm going to state that again in this simple example, okay? So I know that A times B over C is some integer D. I know that B does not have C as a factor. That forces that C is a factor of A. And we need to just go through a little bit of convincing of this fact to yourself. Otherwise, it would be very difficult to see why this is true. Now, since Q to the n and P share no factors, or that means that P is not a factor of Q to the n, this forces that P is a factor. And we have the one result. And the other argument is very similar, is a factor of A sub 0. And that's one way. Now, the other thing we want to show, is that we want to show that Q is a factor of A sub n. And we use this same relationship again. So let's erase again. So now I'm going to erase here. I'm going to erase from when I divided by P. And now I'm going to just divide by Q instead. So when I divide by Q, right, so Q sub n, right, if I divide everything by Q instead of P, right, what's the thing that results? So now I'm dividing everything by Q. And even over here by Q, of course, I divided the left-hand side by Q, but this is still 0. And that's what's nice about 0. Anyway, so now I divide by Q, and I get A sub n over P to the n over Q plus E sub n minus 1, P to the n minus 1 over, this is Q, so I'm dividing by Q, so what do I have over here? I have, nothing, right? Because this is Q to the 1, so it's just this, plus dot, 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 going down, A sub 1. Q to the n minus 1 is Q to the n minus 2 now, P1, plus A sub 0, Q to the n minus 1. And again, I make a similar argument. This whole thing is an integer, right? Integer. So let's minus this over to the side to make a conclusion, right? Minus this on both sides. This cancels. This whole thing is an integer. So then that forces this on the right-hand side to be an integer, right? I just made it a little bit more clear. This whole thing should be an integer, right? This is an integer. P is an integer, so P to the n minus 1 is an integer. An integer times an integer is an integer. And you make the same argument for all of these terms. An integer added to an integer added to an integer is an integer. So then this must be an integer. So A sub n, P to the n over Q is an integer. But again, since Q and P share no factors, right? P to the n and Q share no factors, or that Q is not a factor of P to the n. Therefore, we're forced by the same logic that Q is a factor of A sub n. and we're done. Okay, this is the whole proof. You could put this to illustrate that you made your proof. But that's the idea. Go through this over and over, see what's not clear. Okay, understanding this the first time is difficult because you need to understand when something is and is not a factor. That is the most difficult aspect of this.